At some point in the next week, whether it be on your practice question assignment that you're going to get tomorrow on this stuff, few questions that we do online, whether it be on your quiz that you're going to have on Wednesday on this stuff, or whether it be on your unit assignment that's going to be due on Monday, or your unit test that's going to be on Tuesday, at some point on one of those four things, you're going to be asked to define an electric field. Can anybody define an electric field for me right now? Yep.
It's a field where protons would go, not protons, positively charged
Yep.
atoms would go. Basically, produced by a producer.
Yep. Yeah, it's good. It's an area, it's a region in which a charged particle would experience an electric force if that charged particle was there. So a region in which a charged particle would experience an electric force, that's an electric field. Now, we define the direction of the electric field. You're going to have to do this on all four of those things, okay, in one way or another. Know the direction of an electric field. If I have a positive particle, the direction of the electric field is which way? It's away from it, right? And the reason that it's away from the positive producer is because the electric field direction is defined as the way that a positive particle would move if placed in the field. And if I put a little positive particle there, it's going to move away from the positive producer. Therefore, the field has to be away from the positive producer. Similarly, if I put a negative producer right here, the field is going to point inwards towards it, because if I put a positive charge in that field, it's going to move inwards towards it. It's going to be attracted to that negative producer. Okay, it's the direction in which a positive particle would move if placed in the field. Now, I could easily put a negative particle there, and that negative particle would move opposite to the direction of the field. It doesn't change the direction of the field. Field's still away from the positive and toward the negative. We're just saying that a negative particle would move opposite to that field. Let me draw another field. Let me draw a field this time that doesn't have a producer. We've just got a field that's pointing up and to the left here. Maybe it's caused by a positive, maybe it's caused by a negative, or maybe it's caused by both. That's not really relevant for this situation here. Okay, what I care about is the field itself. If I put a positive particle in that field, which way is the force on the positive? Which way is the force on the positive? Up and left or down and right? Up and left, because it's with the field, right? The electric force is with the field. Now, if I put a negative here, which way is it going to experience a force? Yeah, which way?
It's going to go down and right.
Yeah, opposite to the direction of the electric field. So it's going to be down and to the right. If I put let's say I put a negative particle right here, it's moving this way. Okay, it's moving perpendicular to that field. Which way is the force acting on it this time? Negative particle, the force is acting opposite to the direction of the field, right? Now, what's the shape of the path? It's going to go somewhere in between here, and it's going to look something like this, right? What's that called? It's a parabola, right? It's just like projectile motion that we did back in Physics 20. Let me draw a couple more field diagrams here. This time we got a positive, we got a negative charge really close to each other so that they affect each other or interact with each other. The field surrounding the positive goes away from the positive. Surrounding the negative, it goes toward the negative. I could draw more field lines, but I don't really need to for this one. What do we notice about the field lines that are in between the positive and the negative charge here? Yeah, they're going to connect. They're going to join up. Unlike the field surrounding two positives or two negatives, where the field lines between those two charges repel each other or don't connect or don't join. By the way, if I do two negatives, the shape would be exactly the same. It would just be pointing inwards instead of outwards here. Remember what we said when we drew these the first time? If the field lines connect like this, then we have a force of attraction. If the field lines don't connect like this, then we have a force of repulsion. Right? Good? All right. We had some equations that we learned for electric fields as well. Two of them, in fact. E is equal to kq over r squared, and E is equal to F over Q. I'm not real concerned about the absolute value signs, but I am pretty concerned about this. I mentioned this last week. Why do we want to make sure that we put the little vector sign over top of that electric field? If we don't, I'm telling you, every single one of you will mix this up with energy. Every single one of you will do that at least once. Okay, if you think you're too smart to do that, okay, you're wrong. You will get it mixed up with energy at some point. And right now you're looking at it like, how could I possibly get that mixed up with energy? Because these equations are nothing like energy. You will. I'm telling you, as time goes on, it's going to happen unless you put the vector sign over it. Now, you may still mix it up with energy, even by putting the vector sign over it, but you're less likely to, because a lot of times you're going to look at that and say, oh, I can see clearly that that's different than E, right? If you just call it E, you're just going to mix it up. If you put the vector sign over it, then you might see the difference between these two things. Okay, first one, called the producer equation, if we know something about what causes the field. Second one is the experiencer equation, if we know something about what experiences the field. Our homework last night was worksheet number 8, 1 to 7. We're going to do 2, 3, 4, 5, and 6 from there. Number 2 says, calculate the strength and direction of the electric field 300 millimeters to the right of a negative 2 Coulomb charge. I'm going to circle that millimeters to draw my attention to that, to remind me that I got to convert that to meters. And I want to find the electric field strength to the right of this charge. This is a producer, so we're going to use the producer equation. E is equal to kq over r squared, 8.99 times 10 to the 9. Now, this is a negative charge, but we're going to drop the sign of the charge when we plug it into the equation, just positive 2. Divided by r, it's 0.300 meters. Got to square that. We calculate that value, it works out to be 2.00 times 10 to the 11 newtons per coulomb. Now, it also asked for the direction. If it said, what's the magnitude, then all we need is that value. If it said, what's the strength and direction, or if it even just said, what's the electric field? It's a vector, so we need direction. What's the direction? Let's draw a picture here. We got a negative charge here. The field points toward a negative charge. All we really care about, though, is the field to the right of that negative charge, right? At this point right here. Which way does the field point, Chase, at that point X? To the right of that negative charge. To the left. So draw your diagram for the positive or negative producer, whatever it is that you have. Put your little X at where you're trying to find the field, and then just look at where your arrow points, to the left or to the right. Does that make sense? Chase, does that make sense?
Yeah, kind of. It's just that question number 1 also like the right.
Okay, so let's look at the direction in question number 1 as well. We won't worry about the magnitude in number 1. It's a positive charge. So the field surrounding a positive charge points outwards, away from it, right? As opposed to towards it. Now we're trying to find the field to the right of it. So at point X here, at point X, to the right of the charge, which way does the field point? To the right. It points to the right because it's away from positive. Here it points to the left because it's toward the negative. Okay, let's take a look at number 3. Similar question again. What's the strength and direction of the electric field? 8.5 centimeters to the left of a 300 microcoulomb charge. E is equal to kq over r squared. Q is 300 times 10 to the minus 6. R is 0.085. Then we got to square it. Solve for the value of E, and it works out to be 3.73. Times 10 to the 8 newtons per coulomb. Okay, there's my magnitude. Some people would argue that's the easy part of it. Now the direction, we got a positive charge here. Field points away from the positive charge. We want to find the field strength over here to the left of that positive. Chase, which way is the field pointing to the left of that positive? To the left, yeah. So that field is pointing to the left because it's away from the positive. Is that making some sense? Good. Yep.
Can you show me the calculation?
Yep. So we have in question number 4. Sorry, question number 3 it was. We've got 8.99 times 10 to the 9 times my charge here in number 3 is 300 times 10 to the minus 6. We're going to divide that by, let's use some brackets on the bottom here. Don't really need to, I guess, but we will. 0.085, or we could say 8.5 times 10 to the minus 2. And let's square that. We end up getting 3.73 times 10 to the 8.
Is 300 times 10 to the negative 6 equivalent to 3 times 10 to the negative 4?
Yeah, it should be, yeah.
That's weird, because I still got the wrong answer.
Okay, so you've entered into your calculator wrong. You've just a data entry thing. Maybe brackets, it may be the thing on the bottom or whatever, but maybe our scheduled help, we could take a look at that, okay?
Okay, then I guess it's
Well, I mean, try it. Make sure you can make it work, because, on a test, it's not good enough to say, oh, you know what, I know exactly what I'm doing. Like I get the right numbers and everything, but I get the wrong answer. That's 0, right? 0 to 1 still. So make sure that you can get that. And if you can't, then maybe during scheduled help, I can give you a hand with that, okay?
we have all these numbers, but yeah, that's fine.
Okay, number 4. 4 says calculate the distance from a 3 Coulomb charge where the field strength is 1.09 times 10 to the 11. Here we're going to use my producer equation again. This time I'm going to solve for R. Take the R squared up by multiplying to get on the top. And then let's take the E down by dividing. Almost there. Now what do you got to do to get R by itself? Square root it, yeah. So R is the square root of KQ over E, which is 8.99 times 10 to the 9 times 1.6 times 10 to the minus 19 divided by 1.09 times 10 to the 11. And we square root that. Let's punch this into our calculator to make sure you guys can enter this properly. Sorry, what is it? Oh, it is 3 coulombs, yeah. Yeah, that makes it a little bit easier here math-wise. Thank you. Okay, let's punch this into our calculator now. We got 8.99 times 10 to the 9 times 3. And let's divide that by 1.09. You don't need brackets on the bottom there if you're using the EE button, right? 1.09 EE 11. Let's square root that. And when we do, we get 0.497 or 4.97 times 10 to the minus 1 meters. All right, number 5. Calculate the magnitude of the field experienced by an electron if the net force is 6.50 times 10 to the negative 16. Clearly, this electron is not producing the charge, it's experiencing the charge. That's why, or the field, I should say. That's why it says, what's the field experienced by the electron? So we're going to use the experiencer equation. E is equal to F over Q. F is 6.50 times 10 to the minus 16 newtons. Q is, it's negative 1.6, but we're going to drop the negative. Do the math there, works out to be 4.06 times 10 to the 3. Now, you weren't asked about the direction. There's no way that you can give me the direction here because you don't know which way the force is pointing. But let's add to this question a little bit. Let's say the force is to the right. Which way would the field be pointing if the force was to the right? It's a negative particle. It's an electron. It's a negative particle. Okay? If the force was to the right, then the field would be to the left. Because for a negative particle, the force and the field are opposite to each other. If it was a positive particle, the force would be in the same direction. as the field. You weren't asked that, right? But clearly you could be asked that at some point on a quiz or a test. Next question, the last one that we want to go over here, number 6. Calculate the magnitude of the electric field experienced by an alpha particle, which is a positive particle, if the net force is 2.00 times 10 to the negative 16, and what's the initial acceleration? It's experiencing the field. The force is 2.00 times 10 to the negative 16 newtons, divided by the charge, which is on your data sheet, 2e, or 3.2 times 10 to the minus 19 coulombs. Gives me a field strength of 6.25 times 10 to the 2. Now, doesn't ask me for direction again. Let's say, though, that the force is to the right. If the force is to the right, then the field is to the field is to the, no, to the right. Why was the field to the left here? Why is the field to the right here? Why is the field opposite to the force in this question versus with the force in this question? Yep. Good, because an alpha particle is positive. The field and the force are in the same direction if it's a positive particle. Field and force are opposite if it's a negative particle. Right? Right, Owen? Good. Now, what about the acceleration? All we're going to do for this is say A is equal to F over M. And you already got the force given to us, 2.00 divided by the mass. And that just gives us 3.01 times 10 to the 10. You got meters per second squared. We could say newtons per kilogram, either one. Usually we say meters per second squared though, right?